Here's problem 3528. A monochromatic single frequency, single wavelength light ray in air, index refraction 1, enters a glass prism, index 1.5. In the glass prism, what happens? Well, we have glass, which will be our second index, 1.5, and we have air, 1.0. And we have some light coming in. It encounters the glass, and something like this happens. Speed changes. But we can't have a bottleneck at the interface. So we can't have a buildup of frequency there. We can't have a change of energy or energy loss at the interface. So it must be true that the frequency in medium 1 is the same as the frequency in medium 2. Hence, the velocity, which is in medium 1, is equal to the velocity of light in a vacuum over the index of refraction of medium 1. This would be the wavelength of light in a vacuum times the frequency in a vacuum over the index of refraction of the medium 1. And if I look at medium 2, that velocity will be the speed of light over the index of refraction of medium 2, which is the wavelength times the frequency in a vacuum divided by the index of refraction of medium 2. If I were to divide both of these equations, realizing that the frequencies were the same, and for that matter, the wavelengths would be the same in a vacuum. But this is basically the wavelength in medium 1, which is the wavelength in a vacuum divided by n1, over the wavelength in medium 2. So the change in our velocities, which is equal to n2 over n1, is also the ratio of our wavelengths in medium 1 to medium 2. So the reason our velocity changes is because our wavelength gets shorter. So here's wavelength 2, and here's wavelength 1. And hence, because the wavelengths change, the velocities change, the frequencies remain the same. So our answer on this one is the frequency is the same, but the wavelength is smaller in the glass than it is in the air.